Good afternoon, everyone.
We'll let the people know that you're in the meeting. And oh yeah, the guy is on, eh? He's on.
Yeah, but if I click on to join us, I can't get anywhere.
Yeah, well,
All right.
what can I do? There's not, yeah. Yeah.
Hi, this is Ralph from Enphase. I have Richard Birt with me, so I can introduce him to the chair.
Hi, Ralph. Good afternoon, everyone. Thank you very much for joining us. Birt is gonna lead the meeting. Yeah, it's gonna support me. I do not have a voice today.
Thank you very much, Dr. Etabile. Thank you, Ralph. Unfortunately, the cold weather up north in Gauteng has resulted in our CEO of S.A.F.E coming down with a cold this morning. So please do bear with us as there's a slight change to the order of events and those presenting. So please just bear with us as we manage this. I think we will just allow just for a few minutes, just for those who are coming in a little bit later, just to join us. For the moment, while we just give everyone an opportunity to join in, I would just like to share some housekeeping rules with all of the attendees. Firstly, we would ask that everybody keeps their microphones muted to prevent any background noise or unintended volume coming through. And then secondly, if everybody could keep their videos turned off, their video feeds turned off, besides those presenting, obviously, just to make things run a little bit smoother. Then if there are any questions to be raised during the presentation, please raise that in the chat. And during the Q&A session towards the end of the webinar, we will try our best to work in a chronological order to answer those questions. So if, like I mentioned, if everyone could just mute their mics, then we will just wait for a few minutes before we can start with introductions, and then we can get the webinar going. Thanks all. Okay, I think we can get things going from our side. First of all, I would like to welcome all of the attendees, S.A.F.E members, members of the public. Welcome to this first installment of the webinar series that we've titled the S.A.F.E Solar PV Safety Webinar Series. This is webinar 1, looking at international perspective or international insights on PV safety. We have had, over the past few weeks, there have been unfortunate incidents in the South African solar PV sector with respect to fire and incidents happening. And we felt that the time was right to have this solar PV safety webinar series, focusing on different aspects that make up the safety aspects of a solar PV system. And we are delighted to have Captain Richard Birt from the United States of America to share with us some insights on sort of international best practices and international insights on solar safety, with specific reference to fire safety. I think what is important and pertinent to mention here is that oftentimes South African standards across the board tend to look at international best practices and international examples for guidance, whether it comes to equipment standards, installation standards, safety standards, and so forth. Unfortunately, the fire safety aspect of solar PV systems doesn't allow for that sort of following of a South African perspective. And really the international agencies and international best practices is really in the development stages, looking at solar PV systems specifically. So it really is a privilege to have international insight on this topic that is so important to all of us that joined the webinar today. With that, I will hand over to Ralph to do an introduction to Captain Richard Birt, and then we can hand over to Captain Birt for his presentation. I will then have a S.A.F.E overview or a local overview, and then I think the most important aspect is to have the question and answer session. Before I do that, I would just like to also welcome the newly elected chairperson of S.A.F.E, Mr. Norman Moyo. Chairperson, I don't know if you would perhaps want to do an introduction from your side as well. Then we can hand over to Ralph and Captain Birt.
Thank you so much. Not a lot. I think the focus today is on safety, but just to welcome the members, particularly at short notice, we appreciate. I think the crisis that we have in energy in South Africa, which I term the epicenter of the energy crisis in the continent, just by the mere fact that this is a huge economy, which cannot afford a 30 minutes blackout, let alone a 6-hour or level 6 load shedding. So we do have a serious crisis, but that crisis also presents itself a huge opportunity for us as an industry to leapfrog some of the energy challenges that we had. You could argue that the energy industry or the utility infrastructure that we are currently sitting on is more than 75 years old, has not seen innovation in more than 75 years since the beginning of the utility grid or the ESCOMs of this world. But the crisis has now just brought in an opportunity for us to actually introduce new technology that will help us to leapfrog the energy crisis. But in there lies some of the challenges that we are going to see as we accelerate the deployment of renewables and solar in particular. Solar is a very friendly technology for South Africa because we do have the resources, both in skill, talent, in the sun, in the real estate, and also just a perfect storm for all of us. Now, how do we harness that opportunity without creating a hazard for ourselves? Reputation is very easy to destroy. So let's not underestimate the importance of safety in the way we deploy energy. So I'm excited that we've got the first series, and I would like to welcome, obviously, Captain and the teams behind it to ensure that in the process of leapfrogging, we don't create problems that were dealt with 5 years ago in other markets. It's called intellectual plagiarism. You have to copy from the best. If others have already dealt with fires, let's not deal with fires. If others have dealt with safety issues, let's not deal with those. Let's learn from that so that we deal with a different set of problems. So I would like to welcome definitely the members for taking time out of their busy schedules to pay attention to this. We will create a few more of these series to make sure that we really dig deeper into other stakeholders in the ecosystem, because the insurance industry needs to come on board. Our EPC partners needs to come on board. Our financiers needs to understand. But it's very possible that we could deploy more than 10 million panels and you only have got 2 that could have problematic, but it could destroy the rest of the brand of solar that we are building. So I would like to welcome everyone and thank you.
Thank you very much, Chairperson. Thank you for that introduction and for setting the scene. If I could now hand over to Ralph and to Captain Birt for that part of the webinar series. Thank you.
So I won't say much here. Can you hear me, Devet?
Loud and clear.
Okay. I just want to introduce my good friend and colleague who we're from S.A.F.E, South Africa, and we hosted Captain Birt this week in Johannesburg, and we're now in Cape Town. And it's been a pleasure listening to him over the last few days. Ask him to tell you stories about being a fire captain in Las Vegas, of all places, over the years. And he's retired now, and he's consulting to the industry. So it's been an honor. Thank you so much for coming, Richard. And thanks. It's over to you.
Yeah, thank you again. Thank you for this invitation. This is some really important information. So a little bit about me. So I've been a firefighter for 30 years. I was a captain on one of the busiest fire units in the world. Obviously, the Strip is a very, very busy place. It was a technical rescue team. But the solar part, I've been studying solar safety for 20 years. So a lot of people ask, why did I get into solar? Why is that an interest? Well, I lived off the grid for 15 years. I was a pioneer in solar. My first system I designed and built was 2002. So very quickly, I understood this technology, and I understood how it's an amazing technology and it can change the game, but it has to be safe. I realized back then that I could use my firefighter knowledge to understand the solar and apply it at the residential, commercial, and utility grade. So for the last 20 years, I've been involved in research and development within solar, as in fire safety and what are the problems that will be seen on millions of homes and businesses, and battery storage. So what we're going to look at and discuss today is different architectures in solar, what we started with. So going back to the beginning of really solar in the United States, it started with a DC architecture. So basically the string inverter with panels strung together to make high voltage, going to a high voltage DC inverter was the standard. There was no other technology out there. And so that's what we dealt with. That's what we used because there was nothing else. But what we've seen is technology advances, just like battery chemistry went from NMC, a very volatile, very fire dense chemistry, to an LFP chemistry, a lot safer when it comes to fire activity. So the industry is developing. What I do is I want to basically give South Africa 20 years of research and development that we've done, so you can leapfrog the problems we had. We had a lot of problems in the United States. We had a lot of growth problems, and we had a lot of fire problems. And basically, I want to give you that information so you can make more informed decisions. My job is to give you, not to tell you what to do, but to give you informed information so you can make an informed decision. So where we started was, what are the problems with DC architecture? And I'm going to mention AC architecture. AC architecture at the solar level means a microinverter. And so basically with a DC architecture, we said, where are the fires? Where are the fires happening with a DC architecture? We've got millions of them in the United States. So we had an opportunity to go and investigate those fires. Amazon came to me and asked me, why did their roof catch on fire? And we did the investigations. We looked at it and we said, this was the result. So what we're looking at with a DC architecture is high voltage DC is prone for fire. And for this reason, 20 years of research has come up with fire investigations is the MC4 connector is one of the weakest links in a high voltage DC system. There's several reasons for it. One of them is wear and tear. One of it is human error. And so when you look at the connection, which is really the most critical part when you have high voltage DC, 600, 700 volts DC on a residential, 1,000 to 1,500 volts on a commercial, what we're looking at is where are those faults? So when we looked at the MC4 and we pulled it apart on fires, what did we find? What we found was wear and tear or human error on the connection, creating a vacuum, creating moisture in the vacuum, and creating arc fault. Well, what does an arc fault mean to the layperson, to someone saying, I want solar on my home? Well, what it means is we saw high temperatures from an arc fault, from the DC voltage pushing an arc. We went in the lab, we tested it. So we said, okay, one of the weak links in the system is the MC4 connector. So we started looking at roofs. How many MC4 connectors do you have in a system, a string inverter? So that's when we came to the conclusion, how do we get rid of that arc fault? Well, arc fault detection came along. But again, there's so much noise in the systems with frequencies. And if you look at arc faults and how they're detected, what we saw was the arc fault detection wasn't very good. Basically, the arc fault detection said, hey, you've got a fire on your roof. Vodafone said, hey, you've got a fire on your roof. Now you have a fire. How do you turn it off too? So one of the most important things, I'm going to go step by step of what code we wrote to make the industry thrive. So the solar industry in the United States thrives, and it thrives because we did the hard work with the code. And so the industry can basically put millions of dollars worth of infrastructure in that is trusted by the government, by communities, by homeowners, because we did the hard work and wrote the code. What I'm giving you is a gift of 20 years so you can basically get to that point. So arc fault detection was really critical, but it wasn't very good. And rapid shutdown means when there is a problem on the roof, how do you shut that system down? If you have a string inverter with no rapid shutdown or no way to shut it off, when the sun is shining, you create an arc fault, and that voltage from the roof that you can't shut down is feeding that arc. And it continues to burn. It continues. The roof structure could be tile, but you're talking about temperatures of 4,000 degrees Fahrenheit and above. What you're looking at is you're catching other stuff on fire. You're catching roof members. You're catching wood that is underneath the shingles or underneath the tiles. So we said, how do we do this? How do we stop these houses from catching on fire or commercial buildings? And we said, okay, rapid shutdown would be critical, where we can shut down the main power and it shuts down the system. Well, we got to rapid shutdown, but we still had high voltage DC. And so what we looked at is, how do we get rid of the high voltage DC? So rapid shutdown, arc fault detection, and high voltage DC, we had to get rid of the DC. So when we started looking at the industry, we went to a microinverter, AC architecture, and we said, so what's so good about that? And we said, how do we replace that DC architecture? Because in every home, there is no high voltage DC. And so we said, can we match the voltage of a home? So 230, 50 hertz. How do we match that in the solar system? We looked at a microinverter technology. How does that work? So when we looked at Enphase's microinverter and we started testing it and we started doing fire tests with it, we said, okay, so the microinverter lives under each panel. So there's a microinverter under each panel. Okay, what's the benefits of that? Well, the panel has 60 volts DC, around 60 volts, most panels, 60 to 80 volts. You string that together, you get high voltage. But if you put the microinverter underneath the panel, we went, okay, so you've got 60 volts coming out of a panel. What's it turning to under the panel? Right out of the microinverter, 230, 50 hertz. We went, okay, so you've got 230, 50 hertz coming out from the panel at the microinverter. Then how do you connect the panels together? Because that's the problem with high voltage DC and MC4 connectors. The number one fire risk. That's what happened on the Amazon build. They said, okay, now we have 230, 50 hertz. Does 230, 50 hertz cause an arc fault? No, because when we put it in the lab, there's nothing pushing the arc. So it goes to zero. So what we're looking at is not 600 volts pushing an arc. So if there is damage in the cable, it goes to zero and it shuts off. So we said, okay, so you can get rid of arc fault at the panel level where we've seen hundreds of fires by converting it to 230, 50 hertz. The other part was, we said life safety, because that's one of the critical parts of this. The industry's working to put this on roofs. And we said, how do we keep the people who are working with this stuff? This is live right there. Well, if you look at 230, 50 hertz, we tell the industry this from our tests. If you take 50 hertz, you've got 100 chances per second to let go of that power. Now, with high voltage DC, you don't, you have zero. So what you're looking at is a complete shift and change in the safety aspect, not just in fire, but in life safety. Then we said to the homeowners and to the insurance companies, we said, listen, now we can control that high voltage DC. We can take the voltage down to 60 volts DC from the panel. We've eliminated the MC4 connectors and the connections to a high voltage inverter by replacing with 230, 50 hertz. And we've got a system that has built-in rapid shutdown. How does that work? Each microinverter, if there's any faults in the system, what you're looking at is a complete rapid shutdown to modular level. Norman, I was standing at Norman's building yesterday under a carport, and Norman asked me, he said, what happens if there's damage to the cable and we have an arc fault? What happens if he hits with his car the building and the carport, one of the struts that hold the carport? What happens if there's some electricity? I said, you can't turn it off. You can't turn the sun off. That is a difference too with a microinverter. The idea of this is, how do we turn this off for the industry? How do we have a problem on a roof, whether it's a lightning strike, there's a fire from somewhere else, how do we rapidly shut it down? If we can shut the panel down to a modular level, now you're dealing with 60 volts instead of 600 volts. This is a huge step in safety. So we looked at getting rid of the arc fault. We looked at arc fault detection. We looked at the fire risk from arc faults, and we looked at life safety. And so we started building this portfolio and said, how do we write code for that? And so we started writing code. With the battery, the same thing. We looked at the battery technology, and this is critical because the United States, there is not a 95, 97% installation rate with a battery. It just isn't there. Here, everywhere, that's why I came to South Africa, because I want to listen to the industry. It's a 95 to 97% install rate with a battery. So let's talk a little bit about that connection of high voltage, DC, arc fault, no rapid shutdown next to a battery. So we looked at battery chemistry, millions of dollars of tests, 20 years of testing. I've consulted for Tesla, Sunrun, I consult for Enphase. What we're looking at here is battery chemistry, NMC chemistry. The Tesla Powerwall is a good example. NMC chemistry has fire activity. When that electrolyte in the cell, you got a cathode and an anode and a separator and an electrolyte. That's a battery. We won't go into technical details. When that electrolyte becomes unstable, it can go into thermal runaway and can burn. So we said, how safe are the batteries? How's the battery management system? It's brilliant. The battery industry has done an amazing job making a safe battery. The trouble is with high voltage DC that can create a fire, especially at the inverter connection too. The batteries are susceptible to heat damage. So if you have a heat source outside of the battery, what we're looking at is an unstable electrolyte. Now we're looking at thermal runaway. Now we're looking at off-gassing. What are we off-gassing with this electrolyte? Hydrogen, carbon monoxide, carbon dioxide. 30, 30, 30. 30% hydrogen, 30% carbon monoxide, 30% carbon dioxide, and about 10% of a carbon-based hydrocarbons, gases. So what you're looking at is a very explosive atmosphere if it heats up. So we said, okay, coming down from the roof that was causing all the fires, we said, how do we control the arc fault, the heat, the fire down at the inverter? Where's the inverter? Usually next to the battery. So we said, if we eliminate the high voltage DC and where the weak points are in the inverter MC4 connectors, what we're looking at is making a safer environment so there isn't a fire event that heats that battery up. And so what we're looking at here is a fundamental change in architecture. I'm kind of cheating because we started code in 2012. We're at 2023. We have rapid shutdown. We have many, many fire safety codes that match an AC architecture, and we did it for a reason. So my challenge to the industry is to understand what you're putting in people's homes and businesses, and understand the difference between a DC architecture, AC architecture, where the battery is going in the home? And is that battery going to be exposed to any kind of fire event? And is it going to be exposed to high voltage? And the other point too is, if you're putting these in people's homes, the fire service has to be able to respond and put a fire out. If there is no rapid shutdown, the firefighters across the globe are dealing with high voltage DC. It changes their strategies and tactics. So people are shocked when the fire service pull up, there is no way to turn the DC high voltage off. So they go into a defensive mode and they let the building burn, because they're not going to risk a firefighter's life for 600 volts DC and exposure to 600 volts. If you have rapid shutdown in your system, the fire service can turn the main power off, just like they've done, isolate power to that building, make it safe, and do aggressive strategies and tactics. So there's layers to this building, not only to life safety of the person that puts the system in their home, firefighter safety. Insurance companies have got to understand the risks they're taking when they are deploying solar and batteries. The risk to a home increases. It just does. And you've got to look at where are those risks, and they've got to be informed. I am starting to inform the insurance companies. I just did testimony at the European Union Safety Committee on rapid shutdown. What does it mean? And while I was doing the testimony in Holland, they had a DC string fire on a roof caused by an arc fault from a DC high voltage. What happened was the fire service turned up with a lot of equipment, a lot of manpower, and they went defensive, and they ended up burning 4 homes. And the questions started flying. Why didn't they do this? Because they couldn't shut it down. So I want the industry to solve the energy crisis here. I was in a hotel in Johannesburg, and at literally 10 o'clock every night, the power went out. You have the solution for the power crisis. I'm a huge advocate of renewable energy. I have put solar and batteries on fire stations in Puerto Rico after Hurricane Maria. I believe in your technology. The thing is, if you want to thrive, you have got to make it safe, because you don't want the same reputation as the grid. And so to me, what we're looking at is the technology driving this industry is fantastic. The different chemistries in batteries are fantastic. Now it's your job to make those informed decisions on what code and how you're going to implement this. My job is not to come in and tell you what to do. My job is to make you thrive, make you long-term, and get the trust from the residential market, the commercial market, the government, that you can, as an industry, provide and solve this power crisis. But the only way you're going to do this is by doing it safely. And I am open for questions. There's 20 years of research. We have a ton of information to spread, but those are my fundamental, basic ideas. Rapid shutdown, arc fault detection, stopping the arc faults, going to an AC architecture, battery chemistry placement, and not exposing the batteries to a fire risk of high voltage DC.
Thank you very much, Captain Birt, for that insights from the United States, and thank you for sharing your research and the work that you've done. Really interesting insights, and I think the consideration around architecture and the way that architecture is selected, and sort of the pros and cons of going with different architecture types, really is an important point to make, and also to bring to the fore that there are various architecture types and equipment solutions to look at. both from a fire safety risk point of view, from a production point of view. So there are many different aspects that need to be taken into account when selecting an equipment provider or selecting a system type for your application. And I think the most important thing that Captain Birt mentioned is that safety absolutely is paramount for systems, especially when they are installed in residential applications. That is, where it is right in the home. So safety is an absolute high priority for both the equipment manufacturers and the system installers. I will quickly just share some insights from a S.A.F.E point of view, and also just speaking to some of the next sessions coming up in this webinar series. So please, for anyone who has any questions for Captain Birt, please just hold on for another 5 minutes until I'm done with my slides. Then we'll open up the floor for the question and answer session. Apologies, sharing the screen here. If I could just get a thumbs up from someone that the screen is sharing and that it's not in the presenter view. Thanks, Captain. So just as a quick background to the state of the current regulations from a South African context, we'll just quickly run through both the building regulations side, and then also quickly touch on the electric or the Occupational Health and Safety Act, electrical installation regulations, and SANS 10142. This is just as a quick segue between Captain Birt's presentation and the Q&A section. And I think the most important thing just to note here is that this really is the first step in this solar PV safety webinar series. And just to add that we will be getting experts in from industry to speak to all the specific aspects that I will just be touching on here. So from a South African point of view, the act that speaks to fire regulations in South Africa is the National Building Regulations and Building Standards Act 103 of 1977. That is open source, it's open access, so you can go and read through there. The specific section is 17.1E that speaks to the specific fire safety aspects. As we then move down the hierarchy to the standards, the specific SANS standards that will find application when it comes to fire safety is SANS 10400, Section T specifically. And that really speaks to the application where the specifications and the standard really gives a guideline to those practitioners, both from a building design point of view, but also from a fire engineering point of view. And just to touch that, we will be getting a industry expert, Professor Richard Walls from the Stellenbosch University Fire Engineering Department. He will be partaking in this specific legislative and regulatory environment around building requirements for fire safety, and specifically with the application of solar PV systems. He will be touching on that in the next webinar in this series. And then just the next point to touch on is around the Occupational Health and Safety Act, which is where the electrical installation regulations find application. And then below, the lowest level of that is the South African National Low Voltage Wiring Code, which is the SANS 10142 that we know well in the industry. And I think what is really important to understand here is how these different acts, so the Building Regulations Act and the Occupational Health and Safety Act, how they work together when it comes to the incidents of fire with specific reference to solar PV systems. And I think that relationship between the two acts, the regulations and the national standards, need to be understood, and that will be unpacked in the further webinars in this series, so that the risk can be adequately quantified and it can be mitigated by all the different parties that play a role in a solar PV system, looking at the building owner, the equipment manufacturer, the regulator or the installer, and the electrical contractor, if you look at it from that point of view. So just the last point to make on the electrical installation regulations. Really, there are regulatory requirements, and then there are voluntary requirements that can be required from a solar PV installer or a solar PV installation company. And really, this will be unpacked in further webinar series. But just to point that out, that we will be unpacking this a little bit further, and then the last point just to make is that we really need to understand how these different definitions that form part of the electrical installation regulations, how they interact with the national, the building regulations, and also the specific fire standards, in order to completely unpack and understand all of the risks associated with solar PV systems. So I will end there, and then if there are any questions, we can either raise them in the chat box, or we can raise hands and verbalize them. We've got a first question here from Fora van Skalkwijk. Captain Birt, how would you like to manage the questions? Shall I read the questions and then you answer, or do you want to answer straight from the chat?
No, just read the question to me and then I'll answer.
Perfect, will do. So the first question is from Fora van Skalkwijk. He says, rapid shutdown is a product-specific capability, microinverters with power optimizers. The question is, what can and should be done with string and central inverters that will be installed or is already installed from a fire safety point of view, preventing or addressing solar PV related fires?
Great question. So there's a ton of existing. We didn't jump straight to rapid shutdown. We didn't go straight to arc detection and microinverter and AC technology. We started the string. So your ongoing maintenance of those systems is critical. Yes, you can put this stuff on the roof. Yes, it's got a 25-year warranty on that panel. But what we're looking at is the MC4 connectors, the inverters having a lifespan of maybe 10 years at the most. Those are the weak points. So what we're looking at is ongoing maintenance, the commitment to the industry. They put this in, they can't change it. It's working well, but it's critical to look at the maintenance of those systems. And if there is a problem and it is reported, that someone goes out and looks at it immediately. So that's the critical part, the commitment to look after the equipment. You're in an energy crisis because the power grid did not look after their equipment. So that would be one of the most critical for me decisions as a solar company, to do that ongoing commitment of checking your systems.
Thanks very much for the question, Captain. And perhaps just a follow-up from my side is the industry standard is that annual inspection is generally sufficient. That's both from a mechanical point of view, looking at your mounting structure, cable management, and so forth, but also an electrical point of view, looking at electrical connections, also looking at your insulation resistance and so forth. Would you
Exactly.
say that an annual inspection is suitable, or should it be more site or project specific?
An annual inspection, what we found, especially with all the tests that you can do in the resistance world, especially on a string system, is a brilliant way to start. And obviously, if you have a high-end project where there is a risk factor where you definitely don't want a fire, like in a data center, right? Maybe that can be broken up into more of a quarterly. So you look at the target acquisition, right? And you say, this is a critical, you may increase your maintenance. But what we found is that yearly inspection, if it's done right, can catch a lot of problems starting out. Now, what we're seeing is we want the fundamental change to meet the new code. So everything going in right now in the States has to meet this really strict code, because we want to give you the chance to thrive in the sense of within that year, there may be a problem. But what we're saying is what you have on the ground now, that's the best thing you can do to keep it maintained.
Perfect. Thanks very much, Captain. We'll move on to the next question. The question is from Matumba Matebula. He's saying, thanks for the information, Captain. What is your recommendation with regards to positioning of the battery for commercial and industrial systems? Do you recommend having a separate room for it? And with regards to fire suppression systems, is there a system in the market that can deal with the type of fires ignited by lithium-ion batteries?
Great question. So we just did a webinar on commercial, and there was an event in Arizona where the actual container blew up, and it blew 4 firefighters 80 feet out of their turnout gear. They all survived, luckily. But I would say to you that a separate building with adequate ventilation, because the off-gassing is the critical part. And if you can put a deluge system in with water, that would be the better way to go to cool it down. The idea is when you have thermal runaway and NMC chemistry, it is the cooling down effect is the most important thing you do. It's not the fire suppression, because it's an exothermic reaction. It creates its own oxygen and it will burn. The idea is to cool it down so the electrolyte does not react. So separate building, away from any kind of life source or danger, adequate ventilation. And if you're going to use any kind of system, if the fire starts out, it's detected a deluge system. I was in Munich looking at gas detections for large commercial, where if they detected any kind of gas, off-gassing of electrolyte that hasn't caught on fire yet, they open up and they ventilate. That is one of the most critical things you can do, because otherwise you've got a container and it's filling with an explosive atmosphere. So away from the building, adequate ventilation. If you can get a deluge system that puts it out immediately with water and cools the cells down, that's what you're aiming for. Very good questions.
Thanks very much. We've got a next question from Dicky. That's the name we've got here. He says, hello, Captain. How does one monitor or compute arc flash DC detection to solution?
So basically, when you're looking at an arc fault, an arc flash happens in an environment where you have a separation of all the wire, degradation of the insulation, and basically you're creating an environment. Now that can happen several ways. Looking at the MC4, I'll give you the example of the MC4. Now you have to use a special crimper when you make those end connections. You have to use a torque wrench, but most of the industry is really doing a hand tight and using a pair of needle nose pliers. Let's get real with this. So we said, okay, what's creating that? So when you look at the environment and arc flash, that's where we went to the AC architecture and we went, okay, these are really hard to predict, especially with wear and tear on a roof. Can we just get rid of the arc flash? Is there something we can do where there isn't an arc flash? Well, if you look at the AC architecture, and I challenge you to look at an AC architecture with a microinverter, you're looking at 230, 50 hertz. The AC architecture, when there is a gap, when there is a wear and tear in that AC architecture, the line goes to 0 because there's no high voltage pushing it. You actually get rid of an arc flash in the solar array just by changing a component to a microinverter. That was the holy grail for us in the lab. We said at the end of our test, we said this: if you got stuck on a desert island and you had to make some fire, you are screwed if you've got a microinverter, because you can't do it with an AC and a panel. You give me a panel and a string, I can make an arc flash. That's fundamentally the differences.
I think thanks very much, Dick. I think what's also important to add is that a lot of the equipment coming out, sort of new inverters, both at a residential and a commercial and industrial scale, have that earth insulation, that detection feature built in. So a lot of the inverters will actually run a insulation resistance test every morning before startup. And if there is an adverse reading that could indicate cable damage that could result in that DC arc, the system actually will either not start up and power up, or it will actually release a warning that would enable O&M technicians to go onto site and identify that damaged cable. So there are equipment solutions to that problem. Just wanted to add that as well.
Yeah, and the one thing on that, this is a great discussion, because when we looked at the built-in arc detection in the inverter, we said this is great that we can look and see the resistance and you may be able to catch it. But the trouble is, what we looked at was the frequency noise, and an arc fault detector works by a frequency, and it's a very narrow band of frequency. The noise coming from the system was tricking those things. And I felt sorry for the industry, because they were pushing out the arc fault detector in the inverter, but they were telling me we're having truck rolls and it's a misfire. It's a misfire because of the frequency. So as an installer, I want you to understand that's a great piece of equipment, but that's why they built in so many starts. There's starts and restarts. The reason they built 3 of those in a 24-hour period is because you're getting full starts. So I didn't want the industry to tie up trucks on an arc fault when they're doing their due diligence. They're doing their best, saying, well, we've got this detection. So you've got to understand that the frequency where the arc fault lives in and the noise coming from a system. So that was the other thing we looked at, because I felt bad for the industry. They committed to this. It was a very good step. But man, were they having truck rollouts when they didn't need it. And that's huge to the bottom line to an installer. And to me, that's the ground game. For me, those are the guys that are going to make this work. Does that make sense?
Perfect. Thanks, Captain. I think we'll, in the interest of time, we'll move on to the next question. It's from Edward McCallan from Voltalia, South Africa. He says, hi, Captain. What are industry standards for fire protection systems within the solar field, actual site area? So I think Edward is referring to the actual PV array. And I'm assuming this is a utility scale system. So it would be either a ground mount, fixed tilt, or a single axis tracker system.
So what we teach especially in the fire service with our large ground mount arrays, we're looking at not going to a microinverter technology. We're keeping it at string, because obviously the cost is insane when you start looking at that size. So what we're saying is, if we contain that to an area, we fence it in. And basically at this point, what we're saying, if the asset catches on fire, what we're looking at is, how do you put it out safely for the fire service? And we teach multiple ways of putting it out. It's a very safe system. The ground mounts, I like the ground mounts. You make sure it's fenced off. You make sure it's an area that doesn't catch the rest of the countryside on fire. You keep the grass short. It's a very, very solid, safe system. We are very happy with our large, because nobody's going into there in a fire. At this point, the fire service does a very defensive, putting some water on it from a long distance, or they put an airdrop on it. So to me, the ground mounts aren't the problem. We've got to understand life safety and buildings. That is a completely separate asset. And if it burns, and the asset is just the solar panels, the framing, and the wiring. It's not life safety. It's not a company's business. The building's not burned down and they lose their business. So we're very happy with the ground mount. It's good to hear a question because you guys are doing it right. Just fence it off. Teach your local fire department not to go in there and to do a defensive measure.
Perfect. Thanks, Captain. Thanks for that response. There's a question for me. Okay, wait, no, let's ask questions of the captain first, and then I will answer Tawanda's question at the end. So the next question is from Stephen Thorne. Can you provide a quick overview of preventative maintenance of MC4s, resistance versus thermal cameras, as an example?
Yeah, I would say the resistance testing and the thermal camera, if you've got tools that you can use, the biggest thing for me is the industry knows how to test it. The biggest thing is making the commitment to the test. If you get crazy busy and you're installing, it's really hard to keep that commitment. I've seen the industry, once we prod them with code, once we prod them with these problems, if they can make that commitment with the tools they have, I'm saying those valuable tools you have, and you know your systems, you use the tools, and there's a varied amount of tools, but that's where that personalized system comes in. If you're an installer and you're doing different systems, you kind of know what the maintenance is. So for me to give a big brush of a maintenance, I would say it's this: stick to that ongoing maintenance plan, use the tools for your specialized and different systems, and you'll be in a success. You'll keep that safe, and you'll be able to work towards changing it and building the newer technology. Think of the car industry. The car industry could have stopped at seatbelts. This is a great analogy. This is what I've used for 1,000 installers around the world. The car industry did not stop at the seatbelt. It was a very, very good device. But what did they do next? Airbags, passenger airbags, side airbags, roof airbags. I was on a specialized unit that cut people out of cars. We literally went from people dying in a high-speed crash to them standing on the side of the freeway with the car completely destroyed because the technology got better and better and better. Use the car industry as an example for the solar industry. The technology's there, just get better and better and better.
That's a great analogy, Captain. Really, really like that. And I think that's something that we, as the solar industry in South Africa, can take as a takeaway from the session today. I think the other thing, Stephen, to add from a really practical point of view around MC4s, it's to ensure that your staff is adequately trained to crimp MC4s, use the right equipment, especially staff that is transitioning from a traditional AC electrician contractor background into a DC background, to understand the differences in crimping approaches of a DC cable with an MC4 connector versus a standard stranded AC cable and a lug. There is a difference, and the risks involved if you crimp a DC cable and MC4 connector the same way that you crimp an AC cable really needs to be understood, and it needs to be transferred to the staff. So I see we've got one last question to the captain, and then I will go to Tawanda. If time permitting, we'll add another question. So this question is from Leewell Color. He says, hi, are inline fuses and fuse boxes a sufficient protective measure to help prevent fires on the DC side? My issue is generally DC fires aren't caused by short circuit currents, as most panels short circuit currents is 14 amp, and fuses are generally rated between 16 to 20 amp, which won't be blown by the panel's short circuit current.
So where we're seeing the main fire risk is up on the roof. It hasn't got to the breaker yet. And the arc fault that happens is the wear and tear, either misconnection before. And so when you have that wire damage, you have a positive and negative string coming off a string, and you may have multiple strings on a roof with a positive and negative wire. What we're looking at on the cabling is we're looking at pigeon damage, we're looking at rodent damage, we're looking at wear and tear, we're looking at wind, we're looking at any kind of fault in that system before it gets to that breaker is where we're finding the fire. Now, if it gets to the breaker and it's in the problem with the combiner box, yes, we have a combiner box where the breaker sits, and yes, we've seen fires in there, but what we're looking is that fundamental architecture of stringing this on a roof before it gets to that breaker. That is where we're seeing that fire risk.
Thanks very much, Captain. I think I will quickly touch on the question from Tawanda, and then if there's any last questions, please pop it down in the chat, and then we can touch on that before we wrap up for today. So Tawanda question goes: thanks for this informative platform, Talyard, aimed at me. What is the safety net for installers and general public regarding fly-by-night inverter brands flooding the market? I have seen one literally burn out. Is there a live watchdog regulation? What is popping up on the market, or regulating what is popping up on the market? Thanks for that question, Tawanda. I think it really is important. It is stress that the fire risk of a solar PV system has two components. There's both an equipment risk, and there's also the installation quality risk. And these two aspects need to be managed very carefully, especially when the cause of the fire is being determined. Oftentimes, an installation company can be blamed for a fire incident when it wasn't necessarily their fault, or the equipment can be blamed when it wasn't necessarily the equipment fault, but an installation fault. So I think it's really important to remember those 2 points. In terms of the safety net that is concerned, the work is ongoing with the National Regulator for Compulsory Specifications to bring minimum standards, both safety, equipment, and so forth, into the South African market to ensure that only inverters and solar PV equipment that meet those minimum standards are important and brought into the local market. But in the interim, while that NRCS National Compulsory Specification is being developed, the metros and the municipalities have it within their jurisdiction to impose specifications on systems that wish to connect to their network. The specific specification that I'm talking about here is the NRS 097-2-1 specification, which is a specification that speaks to the way that the inverter interacts with the grid, but it is a really good indication of quality as well. In sort of the normal terms, it's referred to as the City of Cape Town approved inverter list. And what that approved inverter list speaks to is an inverter that has a test certificate that indicates that that inverter complies with the NRS 097-2-1 specification. So that is a resource that is constantly updated, and a lot of the municipalities and the inverter manufacturers actually look to that list and want to get their inverter on that list because it speaks to the quality of the inverter.
Yeah, I just want to add one thing. because I'm embedded in the solar industry in the United States, and their interests are my interests too. That's why I work so hard in the fire testing. What we found too was we literally had to write code to get people to do the right thing. Whereas here, what I'm saying to you is there's a big picture to this. And so those people that are looking at a price point, you've really got to do your due diligence on the architectures, on the equipment you use. That's critical for long term. There are always going to be 5% of you that it's going to be a money thing, nothing else, no commitment. And that will drag the rest of you down. The thing is, how to solve that is if you put in place and work really hard as an industry to bring up your codes and to bring that level, you'll get rid of those people and it won't bring you down.
Perfect. Thanks very much for that input, Captain. It really is. It has been a privilege to have you on the webinar today, the first in our series, Solar PV Safety Series, looking specifically at fire safety, but also branching out to general electrical safety for solar PV systems in South Africa. Thank you very much from the S.A.F.E Secretariat and from the members for the inputs. I really appreciate your time. To the chairperson of S.A.F.E, Mr. Norman Moyer, thank you very much for giving us your time to join in today. Do you want to end off with a message, or can we close it here?
Yeah, no, thank you so much, Duet, and thank you, Captain. Thank you, members. It's been a very engaging conversation. I believe this has been recorded, so it's very important that I think as the recording is shared, let's spread the messaging beyond our members. A strike in one is a strike in all. I sound very Ukrainian right now, so we cannot afford to allow any adulteration to happen on this journey, because it is going to be very difficult to recover from there. So I would like to thank you all. Let's extend the beyond to some of our extended partners, whether it's our insurance partners, whether it's our OEMs, and everyone that we work with. We're going to work as S.A.F.E. We will try to make sure that some of these, we lead the conversation in drafting some of these regulations to make sure that we don't spoil a very good opportunity that we have. But what we have seen with new technologies is, as an industry, we have to lead that conversation. We might have to write the code and work with the government and different stakeholders to achieve the same. And I see this also expands into storage and other different adjacent technologies. So thank you so much. We know you, it was a long flight and you have been all over the roads. We appreciate your time. We might call on you again in future, but thank you, and thanks to S.A.F.E, we have also made this possible, and for supporting us on this journey. Thank you. Have a profitable week ahead, and have a good weekend. Thank you.
Thanks very much, Chairperson, and thanks to everyone that joined in. We hope to see you in the next installment of the Safety PV webinar series. Hope everyone has a safe and restful weekend. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.